Imagine a function on an interval. If you want to find the area under its curve, you might partition the interval into smaller pieces, calculate rectangles, and sum them up. Now suppose instead that the function behaves wildly jumping discontinuously between 0 and 1 at every rational number. Since traditional methods rely on orderly behavior at partition points, they fail completely. In the late 19th century, mathematicians believed that integration was a fully solved problem, confined only to continuous or piecewise continuous functions. And they used Riemann's elegant definition to justify why certain pathological functions simply couldn't be integrated. In other words, these wild functions with dense discontinuities were beyond the reach of calculus. Little did they know that just decades later, a young French mathematician would flip this limitation on its head. Henri Lebesgue would upgrade integration to a far more powerful framework and use it as a foundation of what would ultimately become one of the cornerstones of modern analysis and probability theory. And yet, despite Riemann's elegance, there was more work to be done. In 1902, Lebesgue would crown Riemann's achievements by reorganizing them into essentially a measure-theoretic approach. Lebesgue's theory would prove to be extremely powerful, as it enabled one to bypass the rigid partitioning of domains and instead use flexible partitioning of ranges. Consequently, it would turn many analysis problems from impossible barriers to functions that could be integrated with elegant generality. Let's start by considering the integral of a bounded function on a closed interval, or in mathematical language integration over a compact domain. It's the analyst's go-to model, and arguably the most fundamental of all integration problems. We'll analyze it by first using Riemann's approach, and then Lebesgue's. In this model, the function is bounded. The interval is from a to b, and we're working on the real line. According to Riemann, the first thing we need to do is partition the domain into subintervals. Then, by the fundamental principle of approximation, the integral should equal the limit of finite sums. The function begins at x equals a and extends to x equals b. So initially, we consider the entire area beneath it. We divide the interval into n pieces with partition points x sub 0, x sub 1, x sub 2, up to x sub n. If we choose sample points in each subinterval, then we can form a Riemann sum. Or if we define a coordinate framework, the height at each sample point is, and the width is delta x sub I. The sum is given by the summation of times delta x sub I, which approximates the area under the curve. This just means we're adding up rectangles whose heights depend on where we sample the function. So the finer we make our partition, the better the approximation becomes. This sum will be our fundamental building block, so we can take its limit as the mesh size approaches 0. Now the exact value we get depends on which sample points we choose, so we can consider both the supremum and infimum over all possible choices in each subinterval to keep things rigorous. And after defining upper and lower sums, we have two quantities that bound our integral from above and below. Since the integral represents accumulated area, whenever we have a partition given by p, we can take the limit as the mesh norm approaches 0 to get the integral. A common way mathematicians write this is as the limit of the Riemann sum. So the limit just represents the refinement process. And if we take both the upper and lower sums, we get the upper and lower Riemann integrals, which are written as upper integral and lower integral, respectively. So comparing these two values, we get the condition for Riemann integrability. This is the criterion. A function is Riemann integrable if and only if the upper and lower integrals are equal. Now, when this criterion is satisfied, the function is Riemann integrable, and the common value is the Riemann integral. We can verify this works for continuous functions. By uniform continuity, the difference between the supremum and infimum on each subinterval can be made arbitrarily small. Then we can show the upper and lower sums converge to the same value, and considering the limit, we see that the difference between upper and lower integrals must equal 0. Going back to our integral, the partition determines the approximation quality. So if we take our partition to be uniform with equal widths, then the Riemann sum simplifies to b minus a, divided by n times the sum of f evaluated at the partition points. So the integral at any partition refinement is approximated by this equation. And similarly, we can also estimate the approximation error at any stage as well. Now, applying this definition, continuous functions are integrable, and even functions with finitely many discontinuities work fine. But the moment we encounter a function with dense discontinuities like the Dirichlet function, which equals 1 on rationals and 0 on irrationals, the Riemann integral fails completely. And since the rationals are dense in the reals, every subinterval contains both rationals and irrationals, and no matter how fine our partition, the upper sum always equals b minus, while the lower sum always equals 0, this approach simply cannot handle such pathological cases. Let's now consider how to analyze this integral using Lebesgue's approach. With Riemann, our starting point was to partition the domain the x-axis, chopping it into vertical strips. But with Lebesgue, our starting point is completely different. We partition the range, the y-axis, slicing horizontally. We begin by dividing the output values into intervals, finding which input values map to each output interval, and then measuring the size of those input sets. The result is a measure-theoretic integral. This integral turns out to be extremely useful, but where in the world does it come from? Now, there isn't one simple reason for why this approach takes the form that it does, but there is a nice way to get a deeper understanding of it. So let's take a very useful detour that I hope will give you intuition for why Lebesgue integration partitions the range, what this measure-theoretic perspective represents, and also why it is extremely powerful for handling irregular functions. One of the first principles of modern analysis is the concept of measure. A measure assigns a notion of size to sets in a consistent way, and here, the fundamental type is Lebesgue measure, which generalizes our intuitive notions of length, area, and volume. When we consider sets of real numbers, we can see that Lebesgue measure captures our intuition. An interval from a to b has measure b minus a. And if we consider more complicated sets, since measure is countably additive, we get a beautiful structure. This quantity is called the Lebesgue measure and is frequently just labeled as mu. At first sight, it might not seem like it would be all that useful, since it just assigns lengths to sets. But it's crucially important in modern probability theory, where measure becomes a probability measure that can be used as a foundation for rigorous probability. But that will have to be a topic for another video. For now, let's take a look at what happens if we instead partition the function's range into horizontal slices. We get this very nice decomposition, and as we consider which x values map to each slice, we identify level sets of the function. So, the Lebesgue approach builds the integral by measuring how much of the domain maps to each output value. Although it's not obvious at this point, it does seem like this range partitioning should at least contain some useful information about the integral. To see exactly what it's telling us, we'll need to consider the integration from two alternative points of view. First, we'll move over to something called simple function approximation. We'll construct step functions here, where the function takes constant values on measurable sets. We can now represent the integral by approximating from below and above. For example, at height y, we find all x where f of x is at least y and measure that set. After refining our partition, we add the contributions from each level, multiplying height times measure. Similarly, we can represent every approximation stage of the function, and if we used a different partition of the range, we would just get different step function approximations. This is all really cool, but things are about to get even more interesting. Instead of just simple functions, let's consider measurable functions whose level sets are measurable. The integration now becomes a question of taking the supremum over all simple functions bounded by our function. In order to make the connection with the Lebesgue integral, as well as to make our calculations cleaner, we'll write this formally using measure notation. And again, we are simply representing different stages by sums over measured sets. So when f is non-negative, the integral equals the supremum over all simple functions below it. When f has both positive and negative parts, we integrate f plus minus f minus separately. This limit process represents the fact that we can approximate any measurable function by simple ones, and the measures of our level sets determine the integral value. Our next step will be to compare these two approaches geometrically, so we will visualize both methods simultaneously. If we think of Riemann integration as vertical slicing, partitioning the domain with thin rectangles standing vertically, we accumulate area by summing width times height for each strip. Now this is just one way to accumulate area, and it depends on using domain partitions as our organizational principle. We can compute the integral in a second way as well. To do so, we implement horizontal slicing Lebesgue's approach. First, imagine slicing the area under the curve with horizontal lines at various heights. Each horizontal strip corresponds to a level set, the set of x values, where the function takes values in a particular range, and the measure of this set varies depending on the function's behavior. The contribution to the integral from each strip is approximately the height times the measure of the level set. And since these horizontal slices and vertical slices both cover the same area, they form two equivalent ways to compute the integral. So, we can equivalently express the integral as the sum of heights times measures in the limit. To make things cleaner, we'll formalize this as the integral of f with respect to the measure mu. Now, while the Riemann approach handles continuous functions well, the Lebesgue measure is powerful because it can handle highly discontinuous sets, and it essentially provides a single framework to determine integrability for far more general functions. So, we now have two different approaches to integration representing two different geometric organizations. For nice functions, they agree, but the key question is, when does Lebesgue succeed where Riemann fails? First, we recognize that Riemann's sums depend critically on the behavior of f at partition points. The upper and lower sums can differ wildly if the function oscillates badly at those points. In contrast, Lebesgue integration depends on the measure of level sets, not on point-wise behavior. And here's the key insight. Since sets of measure 0 don't contribute to the Lebesgue integral, we can change the function on a set of measure 0 without affecting integrability. This is why the Dirichlet function, which equals 1 on rationals and no on irrationals, is Lebesgue integrable with integral 0, which perfectly handles what Riemann integration couldn't touch. Going back to our approximation ideas, we can now understand extremely important results in analysis, the convergence theorems. These are conditions for when we can exchange limits and integrals. In Lebesgue theory, we have powerful tools like the monotone convergence theorem and dominated convergence theorem for function sequences. We are now ready to appreciate one of the key advantages of Lebesgue integration, namely its completeness. Essentially, completeness means that the space of Lebesgue integrable functions forms a complete metric space. In measure theory, this corresponds to the fact that Cauchy sequences of functions converge to integrable limits, and the structure enabling this is the sigma algebra of measurable sets combined with the Lebesgue measure. So now we can see we don't need to worry about partition points in the domain at all. We simply need to verify the measurable structure and integrate with respect to measure. It's then just a matter of measuring level sets to arrive at the integral value, which for Riemann integrable functions gives the exact same result. In fact, for Lebesgue's approach, the measure-theoretic perspective is the really fundamental thing here. For different functions, we measure different level sets. But the Lebesgue integral that agrees with Riemann for nice functions uses Lebesgue measure on the reals. This is why the Lebesgue integral frequently seems to just appear out of nowhere in textbooks. It's simply the integral that works when you need to go beyond Riemann's limitations. And in general, throughout analysis, the Lebesgue integral is the one that handles almost everywhere properties and enables powerful convergence theorems. Now, as we saw in each of our approaches, both the Riemann and Lebesgue methods for integrating well-behaved continuous functions are straightforward and give the same answer. But as you consider more and more pathological functions, it becomes extremely frustrating and sometimes downright impossible to apply Riemann integration. You simply can't control the oscillation at dense discontinuities. It is in these cases where Lebesgue's approach makes things not just easier, but possible. Consequently, for most modern analysis problems, the best strategy is to use Lebesgue integration as it allows for vastly more generality. The recipe is straightforward. Verify measurability, write down the integral with respect to a measure, and apply the powerful convergence theorems. Thanks to the transformative work of Henri Lebesgue, integration has evolved from being restricted to well-behaved functions to a powerful measure-theoretic framework capable of handling nearly any function we encounter in modern mathematics.